Hello everyone, welcome to the Institute of Mathematical Sciences and welcome to Chennai. So we are honored to have Professor Parameswaran Ajith for the Institute Colloquium. So I have a lot of text to introduce him, and so the time I'm eating up, he will be getting a little bit extra towards the end. So Professor Parameswaran Ajith is a leading figure in gravitational wave physics and astrophysics, currently serving as a professor at the International Center for Theoretical Sciences, ICTS, as you all know, TIFR in Bangalore. A prominent member of the global gravitational wave community and part of the LIGO-Virgo collaboration since 2004, Professor Ajith has significantly shaped our understanding of the universe through gravitational wave detection. So he did his PhD in 2007. He earned his doctoral degree from the Max Planck Institute for Gravitational Physics, Albert Einstein Institute, and University of Hanover. His thesis received honorable mention in the prestigious Gravitational Wave International Committee's awards. He did two postdoctoral research. He continued his research journey at Max Planck as a postdoc in between 2007 to 2008, and then he joined Caltech, where he was there for 4 years, 2009 to 13, working on waveform modeling and relativity. Then, as a faculty, he joined ICTS TIFR in 2013. Since then, he has received the DST's Ramanujan Fellowship 2013 to 18, led the Max Planck Partner Group of Astrophysical Relativity 2015 to 18, and headed the Indo-US Center for Exploration of Extreme Gravity 2016 to 18. Regarding his contributions, Professor Ajith pioneered the phenomenological approach, combining analytical and numerical relativity to model gravitational wave signals from binary black holes, a method now integral to the LIGO-Virgo data analysis. His work contributed to the landmark discoveries such as GW150914, as you all know, and rigorous test of general relativity. He was part of the teams awarded the 2016 Special Breakthrough Prize and Gruber Cosmology Prize. Further accolades include the Tuas Cass Young Scientist Award in 2020, election to the Indian Academy of Sciences in 2024, and fellowship with the Indian National Science Academy. In his talk today, Gravitational Wave Astronomy Today and Tomorrow, he will discuss the current state of gravitational wave science, results from LIGO-Virgo, the field of pulsar timing arrays, and the future roadmap of next generation detectors. So without further ado, I would give the stage to Professor Ajith.
Thank you very much, Dheeraj, for this overly kind introduction. Very pleased, very glad to be here, sharing the latest news on gravitational wave astronomy. Before I start, I would like to thank the organizers, Padmanath and the rest of the organizers here for this kind invitation. So I understand that this is a mixed audience consisting a number of students from all over India for the summer program as well as the IMSC members. So I would be devoting the first half of my talk to give a broader introduction, and I apologize to the experts in the audience. This will be a lot of two basic things for you, but I hope to say some more interesting content for the more expert audience to the end of the talk. So let's start. So it's fair to say that a lot of things that we know about the universe came from astronomical observations of electromagnetic waves across different frequency bands. And some of these pictures are very familiar to us. For example, this picture of the optical sky, if you look at the sky using an optical telescope. And we are just talking about the newest in this game, which is the Vera Rubin telescope, which is opened up and saw the first light in the last few days. So this is a picture it's a slightly older picture of the optical sky. And what you see here is our own galaxy. So our galaxy is a spiral galaxy, and since we are part of the galaxy, we are seeing a cross-section of that, just appearing as a band, which is the Milky Way. In a clear night, you would see this band in the sky. But if you look at the same sky using a telescope that is capable of observing microwaves, you see a very different picture of the universe. This is what people like Dheeraj works on. This is a picture of the cosmic microwave background radiation. This one is observed by the Planck satellite. So this is basically the relic radiation from very early universe, when the universe was only about 300,000 years after the Big Bang. Now it's about 13 billion years. And what we see is a black body spectrum. The universe was a thermal radiation, which basically you can see as a black body spectrum. And because the universe has been expanding since then, this radiation has cooled down. And now we see this at a peak temperature about 3 Kelvin. So wherever you look at the sky, you see this radiation coming from all directions. It's a remarkably same intensity and same temperature. But there are extremely small fluctuations in the temperature of the radiation coming from different parts of the sky. These are shown as these red and blue spots, these slightly warmer and slightly cooler spots. And we have some understanding. This is basically the baby picture of the universe. And we have some understanding that how the universe evolved from these small perturbations and matured into the current universe, having these large galaxies between and these large intergalactic voids. And we have some understanding of the structure formation from these initial conditions. Similarly, if you look at some of the high energy part of the sky, we see very energetic phenomena. For example, black holes accreting gas, and these accreting gas gets heated up and produce X-rays. This is seen as as X-ray candidates by these XMM Newton Observatory. There are a much more advanced version of this, etc. But the point I was trying to make is that depending on this frequency of the radiation that you are using to look, it is giving us access to different phenomena. And each of these windows are quite unique. And in the last few hundred years, by combining these different frequency bands, in particular the last century, we were able to derive a fairly sophisticated understanding of the universe. And it's primarily through the observation of the electromagnetic waves. However, there was a major game change in the last century. People started using messengers that are different from electromagnetic waves also to probe the universe. And one example is the cosmic rays. The cosmic ray is a misnomer. It is not a ray of light. These are actually high energy particles. They could be protons or nuclei of heavier elements. And they seem to be coming from the outer space with extremely high energies. And when they come and they hit the nuclei of the atoms in the atmosphere and produce a shower of secondary particles. Here is an artistic illustration of these shower of secondary particles, which could be detected using an appropriate network of detectors. And these detectors could be as simple as water tanks, because when these charged particles go through the water tank, the water, they produce what you call a Cherenkov radiation, which can be detected using these photon detectors, etc. And interestingly, the Indian scientific community has made a major early role in the cosmic ray astronomy. Some of the major discoveries of the cosmic rays was done at our neighboring state in Karnataka. This is a photograph of the Kolar gold mines, and TAFR used to have an underground facility which made some of the pioneering discoveries of cosmic rays. Even now, it is a very active field. In particular, there is an international effort to look for these so-called ultra-high energy cosmic rays. These are cosmic rays of something like 10 to the 18 eV or even higher. Some of this, they are much more energetic than some of the most energetic particles that we could create in the laboratory, even the Large Hadron Collider. So this is a photograph of the so-called the Pierre Auger Observatory in Argentina, and where the detectors are actual water tanks. And they have been observing these ultra-high energy cosmic rays over the last couple of decades. And here is, for example, the sky maps of the arrival directions of these ultra-high energy cosmic rays. These black dots are the arrival directions. It is not entirely clear what is the astrophysical source. Yeah. Okay. So basically, so this is so the whole sky is a sphere, right? But we need to represent this in some two-dimensional coordinates. So just like we make a map of the world, astronomers make a map of the whole sphere of the sky into a two-dimensional plane. And usually, different coordinates, different communities actually have different conventions. So this is the simplest thing called the equatorial coordinate system, where the galaxy is in the x-axis, and this is the north pole of the, this is the north pole and this is the south pole, and each point in the whole sphere can be mapped to a point in this two-dimensional map. So this basically, we are representing the locations on the sphere into these two-dimensional points. So each of these dots are the reconstructed directions of the arrival locations of these ultra-high energy cosmic rays. It is not entirely clear what is producing these ones. There are multiple possible candidates. So there could be supermassive black holes accreting gas and accelerating these particles to very high energies. There could be pulsars, rapidly spinning neutron stars, accelerating these particles. There could be gamma ray bursts, etc. So, collapse of massive stars producing these high energy bursts, etc. So it is not entirely clear. So as an effort to try to, to possibly identify the reasons, here they have juxtaposed the locations of the supermassive black holes, so-called active galactic nuclei, to see if there is any correlation. It is not obvious there is any correlation, but it's also not very simple because these cosmic rays are deflected by magnetic fields, and our galaxy is known to have magnetic fields. So what you see as the arrival directions may not be the true actual location of these in the sky also. So it is, the jury is still out on the question of what the ultra high energy cosmic rays are. Of course, I am not the very current update on this one, so it could have changed the last some time. But I was not aware of this any serious major update on there are actually one candidate which was actually correlated to a supermassive black hole, a blazar, but even that correlation is slightly debated. Another example is the neutrino astronomy, which again is in a very rapidly maturing field. This is a remarkable observatory in the South Pole called the Ice Cube Neutrino Observatory. This is what you see on the top in Antarctica, but the actual observatory is kilometers down. This is a schematic diagram. So what they have done is to draw big holes in the Antarctic ice. And the Antarctic ice is a remarkably transparent object. So when these neutrinos pass through the ice, they produce a Cherenkov radiation. And all these big holes contain a large number of photomultiplier tubes to detect these radiation. And by seeing out which of these PMTs light up, they can even track back the arrival directions of these neutrinos and detect their energies, etc. And here is again an example of the sky map of the arrival directions of the neutrino candidates, neutrino detections by the Ice Cube Observatory. Again, not entirely clear what is producing these GeV or hundreds of GeV neutrinos. Hopefully, you will have more understanding in the next decades. I just want to drive one point that these non-electromagnetic messengers are also quite important because they contain complementary information. For example, the neutrinos are produced in the nuclear reactions that happened at the interior of sources like stars or collapsing stars, supernovae, etc., while the electromagnetic radiation is often produced at the surface or in the atmosphere of objects, etc. So they contain very complementary information. So by combining these two things, one hopes to learn more about this. The last one in this arsenal of the astronomer's arsenal is the observation of gravitational waves. So again, let me take just 1 minute to just briefly introduce what gravitational waves are. The existence of gravitational waves is a prediction of Einstein's theory of gravity called the general theory of relativity, which is the most accurate theory that we have right now. It's a classical theory of gravity. And it basically describes that gravity is not a force, but it is a manifestation of the curvature of space-time. So massive objects, as well as other forms of energy, would introduce a curvature in space-time. It's very hard to imagine or observe a space-time curvature, but it would have a number of possible observable consequences. So one, for example, obvious example reason is that instead of light traveling to a straight line, it would follow the geodesic, the closest curves that are closest separation in 2 points. in these curved space-time. And this was, in fact, the first observational test that kind of verified this remarkable prediction of Einstein's theory by Eddington, the gravitational bending of light. And when these massive objects actually move about, these space-time curvature follows these objects. And it turns out that the information about the variation of the space-time curvature cannot propagate instantaneously because there is a maximum limit in the propagation of the information, which is determined by the special theory of relativity. And these basically information about the disturbances in the space-time curvature are called gravitational waves. So gravitational waves can be thought of as ripples or disturbances that propagate on the space-time. And when you have things like binary systems of stars, which basically you have an accelerating pair of masses, the corresponding disturbance in the space-time actually propagate at the speed of light and produce gravitational waves. There are these characteristics have the gravitational waves have a characteristic nature. They have some similarity with electromagnetic waves. They have two polarizations, but unlike electromagnetic waves, which are described by a vector field, these are described by a tensor field. So basically, if you this animation shows how some free particles basically move when gravitational waves disturb the space-time. Basically, these ring of test particles are tracers of how the space-time geometry changes as the gravitational waves propagate. So here, these gravitational waves are propagating in this direction, and you have this ring of test particles, which are originally arranged as a circle. And when these gravitational waves pass, these circles get deformed into ellipses, so get stretched in one direction and compressed in the other orthogonal direction. These are called quadrupolar patterns. So these changes can be detected using multiple ways, but the most successful way has been using large laser interferometers. And this is a technique that all of you are familiar with. So here is an example and how this can be used for gravitational wave detection. So if your wave is coming perpendicular to this board, initially you have this interferometer, and here is a laser and a beam splitter, and you have two end mirrors, and this laser beam is split into two orthogonal arms by this beam splitter, and these two end mirrors reflect them back, and you produce an interference pattern here. And initially this interference pattern can be adjusted so that this length of these two arms can be adjusted so that this interference is destructive. So you see no light going out of the so-called dark port. But when a gravitational wave hits this interferometer, one direction gets stretched and the other direction gets compressed. So that introduces a relative change, a differential change in the arm length of this interferometer. So this takes a longer time to go and come back, while this takes only a shorter time to come back. So that would result in a change in the interference pattern. So if you look at one point in this interference pattern, you would see a time-dependent change in the brightness of that spot, which can be read by a photodetector. So it's a standard technique, but typically you measure length changes that are order the wavelength of the light that are in a laboratory setting, right? Which is order nanometers if you have optical light. Hundreds of nanometers. So this is a micrometer. So, but the problem is that the expected distortions here due to the passage of gravitational wave are extremely tiny. So the amplitude of gravitational waves is like a strain on this interferometer. So it is like delta L by L, where delta L is the change due to the passage of the gravitational wave, while L is the original length. And what we are trying to measure is the delta L. So to make delta L larger for a given H, given strain amplitude, you have to make the L, the arm of the interferometer, as large as possible. So, but even if you have a kilometer scale instrument, the typical astrophysical sources produce gravitational waves of amplitude of 10 to the minus 21. So even if you have a kilometer scale instrument, the differential change in the interferometer arms is order 10 to the minus 18 meter. It's an extremely small number. It is much smaller than even the size of a nucleus. So it is a very difficult measurement problem, and that is why it took so long. Einstein predicted this existence of gravitational waves, a century ago, but this first experimental evidence came only in the last 10 years. So there was a long, decades of long effort to devise these measurement devices as well as to construct them and to make the measurement. So this finally was made possible by these large instruments called the LIGO in the USA. These are these kind of Michelson interferometers, but very sophisticated versions of that to improve the sensitivity, because you are able to measure. You should be able to measure a very small fraction of this fringe shift due to the differential motion of the interferometers. So these are 4 kilometer by 4 kilometer long Michelson interferometers, which use a very sophisticated optics, extremely high quality optics, hundreds of kilowatts of laser power, and extremely high vacuum, and so on to make these measurements. There are 2 of them in 2 corners of the USA. One is in the northwest and one is in the southeast, separated by about 3,000 kilometers. So because gravitational waves travel at the speed of light, they would take about 10 milliseconds to travel from one side to other. And these redundancies built to make sure that you are actually seeing the signal and not some noise-induced disturbances, too, because you have to introduce this duplication of the same observation. So the LIGO instruments have been actually functioning since early 2000s during their initial generation. But what happened in 2015 was they were upgraded to a factor of few higher sensitivity by putting a new detector in the same facility. And as soon as these detectors started operating, they detect the first gravitational wave signal. So this is a multimedia representation of these first gravitational wave signal. This is the time axis in units of seconds. So you can see this whole thing lasts only for about a half a second. And the vertical axis shows 2 things. These are the actual time series data. For example, how these detectors move as a function of time, calibrated to the units of the gravitational amplitude. So you see this sort of very interesting pattern. This is called a chirping pattern. You have a quasi-sinusoidal signal which has a similar frequency, but the frequency is increasing with time. At the same time, the amplitude is also increasing with time. And it reaches a peak and followed by some sort of exponential damping of the amplitude. This is a kind of a characteristic signal that we expect from the spiraling of 2 compact objects, which could be black holes or neutron stars. These could be formed by various astrophysical mechanisms. So once you form this binary system, they orbit each other, they emit gravitational waves, they lose their orbital energy and angular momentum into gravitational waves, they come closer, and then they rotate faster, and eventually these would merge. So it forms a deformed black hole, and it basically radiates its deformations by what are called quasi-normal modes, and settles into a quiescent rotating black hole hopefully described by the Kerr solution. So you see that this is sort of like a classic signal that one was hoping to detect, and it seems that this data is actually showing that one. And the background shows also like a spectrogram, how the frequency of the signal is actually increasing with time, the same kind of information in a different way. So you see the same signal measured by 2 detectors separated by about 3,000 kilometers. So that gave a lot of confidence that this is not some sort of a local noise source. It is actually an astrophysical signal. And by comparing this data with theoretical models of the expected signals by solving Einstein's equations, one could conclude that this is produced by the spiraling and merger of 2 massive black holes, each weighing about 30 solar masses in a distant galaxy about 400 megaparsecs, about 1 billion light years away. Since then, this of course, this all of you know, the pioneering founding members of LIGO, Ray Weiss, Barry Barish, and Kip Thorne were awarded the Nobel Prize in 2017 for decisive contributions to the LIGO detector and for the detection of gravitational waves. But now, perhaps not many people have not followed the story since then. The story has not ended. In fact, it's the beginning of that. Since then, the LIGO and Virgo detectors have conducted 3 scientific observing runs. The 4th one is ongoing. And during the first 3 observing run, LIGO and Virgo have detected about 100 gravitational wave signals from such merging black holes and merging neutron stars, all happening at different parts of the universe. And this is showing like a cartoon version of the black holes and the neutron stars discovered by LIGO and Virgo through their gravitational wave observations. So this vertical axis shows the mass of these objects, black holes and neutron stars, in solar masses. The horizontal axis has no meaning. So each of this cluster, for example, three blue dots come from one signal, because remember one signal is produced by merger of two black holes, and it eventually merges to form a third black hole. So you can interpret this way. You merge these two black holes, about 25 solar mass and about 40 solar mass, to produce this 55 solar mass final black hole. And if this is not very clear, but if you carefully look and add these numbers, you will not get the final number. So M1 plus M2 is not actually equal to the final mass, because a part of the total mass energy of the system is actually lost into gravitational waves. It's actually significant. It could be about a few percent. So you can see this. It's a remarkably energetic process. Although you cannot see them, it's so weak to detect. These are extremely luminous processes in gravitational waves. And there are all these similarly 100 such signals producing black holes. And there are these orange ones are the mergers of neutron stars producing probably a more massive neutron star or a black hole also. And in between there are these objects which are half marked as blue or half marked as orange. We do not know whether these are black holes or neutron stars. These could be some heavy neutron stars or some very light black holes. In either case, this is a world record in some sense. This could be the heaviest neutron star that we have ever seen, or the lightest black hole that we have seen. How do we know? You can compare this with other black holes and neutron stars that we have discovered from our galaxy using electromagnetic observations through X-ray observations or from radio observations. So these crimson dots are the black holes discovered by X-ray observations. So they do this, these are called from the so-called X-ray binaries, where one normal star is orbiting a black hole, and this black hole accretes this gas in the star and produces X-rays. And by the spectral shape of this, because this is a Doppler modulation because of the motion of the star, you can measure you can put an upper limit at least of the mass of the black hole. And these are the black hole measurements from X-ray observations. So you can note two things. One is that most of these black holes in our galaxy have masses order 10 or 15 solar mass or even less. While a lot of black holes that LIGO and Virgo have discovered, which are extragalactic, which are from distant galaxies, are much more massive. So you are discovering new populations of black holes which astronomers did not know to exist. So until 15 years ago, a typical black hole that an astronomer would think of was order 10 solar mass, because the kind of black hole that we have seen in our galaxy. But now it has gone up to 50 and even 100 solar masses. Similarly, these yellow dots are the so-called radio pulsars. These are spinning neutron stars producing beamed radio emission, which we can observe as pulsed signals in radio telescopes. And your colleague here, Manjari Bakshi, works on this kind of things, and using these also to detect gravitational waves. And I will talk about that a little later. But it turns out that by a combination of nuclear physics and gravity, neutron stars are allowed to exist only in a small mass range, about 1 solar mass to about 2.5 solar mass or so. The exact range is still uncertain, but these ones are kind of questioning our understanding of those ones. So there could be some very heavy neutron stars or some very light black hole that, again, we have no signature of such things in our electromagnetic observations. So just to give you a very quick summary of what we have observed using these observations. There are actually one event that we have. What is the theory? Okay, so one simplest theory is that they could be produced by the merger of lighter black holes. Yeah. You can possibly produce, or they could be produced in the early universe from the collapse of what is called as type 3 star. Type 3 stars, population 3 stars, not type 3. So they are primarily produced of hydrogen. So they don't lose a lot of mass through winds. So such population 3 black stars can collapse to produce so-called population 3 black holes also, which can be about 100 solar mass or so. So these are the first observations of massive black holes, which are more massive than about 25 solar mass or so. And there are some potential evidence of intermediate mass black holes, which are black holes that are more massive than the typical stellar mass black holes, could be about 100 solar mass to about 1000 solar mass, but less massive than these supermassive black holes that are lurking in the center of galaxies. We have this one remarkable observation, which is called a 170817. This happened on the 2017, August 17, which was a merger of two neutron stars. And we not only observed the gravitational waves from that, this merger also produced a flash of electromagnetic radiation, which was observed across the spectrum of electromagnetic waves, starting from gamma rays all the way up to radio. It's a remarkable inauguration of the multi-messenger astronomy, where you observe the same object, same phenomenon using multiple messengers, which includes gravitational waves and the entire spectrum of electromagnetic radiation, and hopefully in the future, neutrinos also. There are some additional candidates of such neutron star and black holes, neutron star binaries in our catalog, but since they have no electromagnetic counterpart, we cannot ascertain its exact nature. There are some of these puzzle objects, which could be either the heaviest neutron stars or the lightest black hole that we have seen. We also have seen binaries with large mass ratios, one large orbit, one large object and orbit, and a small object. And these are not very surprising, again, in terms of fundamental physics, but one could see some interesting properties of gravitational waves in the signal. So, for example, gravitational waves are in the leading order produced by is a quadrupolar radiation, just like electromagnetic radiation is in the leading order a dipolar radiation. But just like electromagnetic radiation can have higher modal multipoles like quadrupole, octupole, etc., gravitational waves also contain contributions from higher multipoles like octupole, etc. And we do see the evidence of these things in these binaries also. So I might be going a bit too fast, but if there are any questions, I can stop for a moment. Yeah.
Just one quick question, like, so this evidence of, I understand that the initial, when you showed that animation of plus and cross, the circular ring of particles getting perturbed, that happens due to only quadrupole or quadrupole higher and so on and so forth? Like, so the ones we are detecting on the Earth is mainly quadrupole nature, right? So if I'm detecting higher multipoles, I should still see that kind of pattern, or?
Yeah, it's I think this quadrupole here is in a slightly different connotation as compared to detector. It is basically what is the radiation pattern around the source, okay, right? So your radiation, if you look at the the energy that is radiated over the sphere from a source, the primary thing is a quadrupolar version, but then higher order multipoles in the radiation pattern. So in practice, it would imprint as higher order harmonics of the orbital frequency in the observed signal. So the imprint of that in the observed signal is that that in the leading order, the frequency that we have shown is twice the orbital frequency. But you would see higher order harmonics of that in the observed time series signal. That is the imprint that you would see of the higher order multipoles in the signal. It is not so much in the quadrupolar deviations due to the passage of gravitational wave.
Okay. Thank you so much.
Sir, we are getting the gravitational waves as a energy loss of two binary stars, right? If that's the case, by that, how we are detecting what will be the mass of two things which are there? If it is loss of energy because of their collision, how we can predict what is the mass of the two objects?
Right. Okay, that's a good question. So it turns out that there is this chirping rate. For example, the rate at which this orbit is shrinking depends on the properties of the system. In the leading order, it depends on any particular combination, but the higher order terms are determined by the individual masses as well as their spin angular momenta, how fast they are rotating, etc. So there are imprints of all this information in the higher order terms of these gravitational waves. So we cannot disentangle all this information, but we have reasonable ways of measuring their individual masses, spin angular momenta, etc. So it's from this chirping rate that is, it's basically the shape of the signal that contains this information. Okay, I guess I'll proceed now. So, okay.
Sir, when we detect a gravitational wave, how do you know which direction it is coming from? Is it the shape? Does it contain the information as well?
It's a good question. So it doesn't. So if you have only a single detector, we are unable to measure the location of the sky. So the only way to do that using multiple detectors, with a separate part of the globe. So by the simple way of doing it is you can look at the difference in time of arrival of the signal to multiple detectors. And since you know the distance between these detectors and you know the speed of gravitational waves, you can triangulate them. So that's a simple idea, but in practice one could do better than that. One could kind of synthesize it, synthetic telescope by combining this data, etc.
Thanks.
Okay, so I'll also give you a quick summary of the interesting science that has come out of these observations in the last 10 years. One interesting thing that these observations allowed us to test the theory of general relativity in a regime of extreme gravity and extreme velocities, because these objects moving, before they merge, they are moving at speeds close to the speed of light. So this is showing an actual a simulation of a numerical by a numerical relativity calculation of a gravitational wave signal from a merging black hole, and this shows their orbital tracks. So this shows, for example, how the separation between the black holes is changing as a function of time, and how the velocity is changing as a function of the units of c. So before they merge, they are moving at speeds close to the speed of light. So what you have is some sort of a cosmic particle collider, right? You have these extremely massive and compact objects moving at speeds close to the speed of light and colliding. They're experiencing extremely strong gravitational fields. And the question is whether Einstein's theory is able to predict the observed gravitational waves. So this is, and so far it turns out that all the observations are indeed consistent with the theory's prediction. So the theory is actually holding up to these observations. And there are different ways of testing these theories. I'm not going to the details. But one simple and very powerful test is using these multi-messenger observations, right? So again, according to Einstein's theory, gravitational waves should travel at the speed of light. But does it? And we do have an experimental confirmation that they do travel at the speed of light with an accuracy within a part of 1 part in 10 to the 15. So the observation is a remarkably simple observation. So there is this binary neutron star merger producing a gravitational wave signal and a flash of gamma rays, and there could be some time delay between the emission of these things. But what we have seen is that after traveling about 100 million light years, about 40 megaparsecs, they reach the Earth with a time delay of like 0.6 seconds. So this means that they have to be travel the same speed within very small error bars, like a part in 10 to the 15. So it is a remarkably simple observation producing a remarkably profound, verifying a remarkably profound property of gravitational waves. And there are many such things that is possible using these multi-messenger observations. Another interesting avenue that these observations have opened up is that these observations are now allowing us to measure the cosmic expansion rate in a totally different way. So the idea is that currently there are multiple ways of doing this one. We know that universe has been expanding, and the expansion also has been accelerating in the last couple of billion years. And there are very precise measurements of these cosmological parameters. For example, the Hubble constant that is primarily responsible for this expansion in the local universe. So one is using the cosmic microwave background observation, like people like Dheeraj works on here, and it is shown by this green curve here. While another method is using the so-called type 1a supernovae. The idea is that there is some way of calibrating these supernovae, this exploding, this merging white dwarfs possibly, and you can measure the distance to that using a series of calibration techniques, and you can also measure the cosmological redshift, and a relation between the cosmological redshift and the distance, luminosity distance, is given by this Hubble's law in the local universe. So that is where these standard candles measure, or standardized candles measure the distance, the Hubble constant. And very interestingly, these coalescing compact binaries are absolutely calibrated standard sirens, or standard candles. You don't need a series of calibrations to measure the distance. Once you observe signal, you can directly measure the distance to the source. Of course, our precision is not that great, but there is no issue of accuracy, there's no issue of biases. And if there is some way of measuring the cosmological redshift, for example, using an electromagnetic observation from the same source, like this binary neutron star merger, then one can actually measure the Hubble constant. And one attempt was actually made using this first neutron star merger event, and this shows the posterior distribution of the Hubble constant from this neutron star observation. And currently you can see that this posterior distribution is very wide. The measurement is not very precise, it's very, very loose in that sense. It contains all the information, the current measurements, but in the future, once we have many such multi-measurement observations, we will be able to combine these measurements to hopefully make a much more precise measurements. And there is an ongoing tension between these multiple measurements, and they independently seem to be very precise, but there seems to be a disagreement between these multiple measurements. This could be a sign of a systematics in one or two of these measurements, or it could be a sign of something fundamental in our understanding of cosmology. In either way, it is important to have new measurements, also multiple measurements, which hopefully have better understood systematics also, and these gravitational waves would possibly contribute to this issue also. These observations also inform the nuclear physics to an extent, and this is the observation of the neutron star, especially binary neutron star. The idea that these neutron stars are made of some very high density soup of nucleons and the neutrons, and the equation of state of matter at this extreme high densities is not known. It cannot be reproduced in laboratory. However, this nuclear physics determines the structure of the neutron star, what its mass and radius, etc. And it also it also affects the tidal deformation of this neutron star. During the last stages of the spiral, the tidal force of the companion can stretch the neutron star into some sort of these droplets. Here is a cross section of an actual numerical simulation of a double neutron star binary. The neutron stars should be spherically symmetric most of the time, but when they are very close, these tidal forces just stretch these neutron stars, and the amount of tidal deformation in the leading order is described by one scalar, which is called the tidal deformability or Love number, etc. It's basically showing the ratio of the induced quadrupole moment to the external tidal field. And these tidal deformation would have an imprint on the gravitational wave signal, because that would determine whether the spiral happens a bit slower or faster. And so far we have not measured a positive value of the tidal deformation in this event, but we have upper limits on the tidal deformation. So this shows, for example, how the tidal deformation of neutron star 1 and neutron star 2 in these binary neutron star event. And here these colors, this density plot shows the height of the posterior probability. So it is more likely that this first neutron star have a tidal deformation between 0 and 500, and the second neutron star have a tidal deformation between 0 and 2000. So this is the measurement that we have. But now, there are many nuclear equation of state models. It's very hard to solve them exactly. It's like a very difficult quantum many-body problem. But there are multiple models of that. Some of them actually predict rather high values for this tidal deformation parameter, like this one. So the fact that the observations are not producing such high values for tidal deformation essentially rules out some of these equation of state models. And in the future, we hope to do this better and better. We can also start talking about population properties of the black holes and neutron stars in the universe. And for example, using this large catalog of events, we are now trying to ask the question, what is the mass distribution of black holes in the universe? What is their spin distribution? How fast are they spinning, etc.? And we see some first results of this one. It's not very accurate yet, but these would become more and more precise in the coming years as the catalog of observations would increase. And this could show, this for example shows the mass distribution of black holes in the universe. So it's mostly a power law, but you see an interesting hump here. It is not entirely clear whether this is a statistical fluctuation, but there are some reasons for having some dips like this here. For example, there is a possibility of what is called a pair instability supernovae. So these black holes are produced by a collapsing massive star, and if these massive stars are in a particular range, it turns out that in a particular mass range, something called the pair instability supernova can happen, which can totally obliterate this whole star, leaving no remnant. So there is a prediction that black holes of certain mass should be absent in the universe from the collapse of stars. So is this a sign of that or something, some other uncertainty? We don't know yet. This one? Yeah. This is the merger rate of black holes of various masses. So you could imagine this, think of this as a distribution of black hole masses in the universe as observed from the gravitation observations. This one's, okay, this one, this is a spin distribution of black holes. So it's a particular combination of the spin angular momentum. So this is suggesting that basically most black holes have very low spins. And the dimensionless units, it's order 0.05 or something. While this shows how the merger rate is changing as a function of the cosmological redshift. So you can also ask questions about other aspects of cosmology also. For example, do we have, what is the nature of dark matter? Of course, the most popular understanding of dark matter is it is produced by some beyond standard model particles, and there have been a lot of searches going on in the lab as well as using astronomical observations. We have not found any evidence of such dark matter particles yet. Another idea is that this dark matter could be comprised of a large number of black holes, for example, primordial black holes, and they could exist in a whole range of masses. Again, this possibility has been heavily constrained by various astronomical observations. But if these black holes contribute a good fraction of the dark matter, they could have various observational consequences in the gravitational waves also. So for example, this shows what fraction of the dark matter could be in the form of primordial black holes of about 1 solar mass or less. Because if these black holes exist in a large number, according to certain models, they should form binaries, and we should have seen mergers of such sub-solar mass black holes. And the fact that we have not seen any object with mass less than 1 solar mass can be used to put an upper limit on the fraction of dark matter in the form of primordial black holes of sub-solar masses. This shaded region is ruled out. Similarly, if the dark matter is in the form of primordial black holes of 100 solar mass to about a few thousand solar mass, they should have produced lensing signatures in the observed gravitational waves. The idea is that we are living these dark matter halos, and the gravitational waves are propagating through them, and because of these intervening objects, the curvature of space-time produced by the intervening object, these gravitational waves are gravitationally lensed, just like electromagnetic waves. And the fact that we have not seen any gravitationally lensed gravitational waves can also be used to put some modest upper limits on the fraction of dark matter in the form of compact objects of this mass range, about 100 solar mass to a few thousand solar mass, or even black holes of this supermassive black hole also. These are modest constraints. This is something not very, very new, but this shows a new way of doing these observations, and these constraints could get significantly better in the next decade or so. Finally, I also want to give us a quick sense of what came of these multi-messenger observations also. These electromagnetic observations from this neutron-star merger have suggested that a large fraction of the heavy elements heavier than the iron, could be synthesized in this neutron-star mergers by a process called the rapid nucleosynthesis process. And there are some evidence of this production of heavy elements in these spectra and the light curves that we observed after this event. So the remaining 5 minutes or 10 minutes, I can give you a very quick glimpse of what is the future of these observations. So I should just stress that the gravitational wave astronomy is only still its baby steps. It is the early stages of these observations. This shows, for example, how the number of detections increase as a function of the space-time volume that we have probed. Now, just the volume of the universe that we can probe using these detectors multiplied by the observing time. So there's a steady growth in these observations, and this shows how the observing plans of these detectors are going to evolve in the next decade. And in summary, in the next decade, we will be observing a few thousand gravitational waves. In the ongoing observing run, we have already observed about 200 gravitational waves. These are being analyzed and published. But in the next 10 years, with the upcoming upgrades of these detectors, we'll be observing thousands of gravitational waves from these guaranteed sources of compact binaries. But apart from that, you're seeing other sources which we have not seen. For example, a stochastic background of gravitational waves from all these merging binaries that are happening at different parts of the universe. We could potentially see spinning neutron stars in our galaxy producing a continuous gravitational waves. If there is a galactic supernova happens in our galaxy, it can produce a burst of gravitational radiation that we can detect. We could also see new phenomena such as the gravitational lensing of gravitational waves, etc. And one particularly exciting thing that would happen, that is for the Indian community, is the upcoming LIGO India project. There was a question about how we can localize this in the sky. So I told that we cannot localize these gravitational waves using single detectors. We have to have a network of detectors, and these are localized using the time delay measurements between different baselines. So if you have a detector that is significantly far apart from the existing baseline of detectors, that would significantly improve the localization accuracy of the network of gravitational waves. So this is where LIGO India can make a significant impact. For example, this simulation shows how this sort of localization accuracies of these existing LIGO Virgo network, even if they reach their design sensitivity. So you see these large uncertainty patches, but with LIGO India, these can be significantly improved. So LIGO India would significantly improve the localization accuracies of this international network, and hence it will make it easier to follow these observations using electromagnetic telescopes. And here is a quick timeline of these LIGO India observatory. This proposal has been around for the last 15 years or so, and finally it got some momentum. The cabinet has approved this full project 2 years ago, and earlier this year, 2 months ago, finally a tender for the large-scale construction has been released, and they are hoping to complete the construction of this detector in the early 2030s, and hopefully join the observing runs in the early 2030s. And here are some signs of what is happening. This is the Rajaram Amana Center for Advanced Technologies building this large facility to prototype this interferometer and to do things like cleaning up the optics, etc. Here are the large vacuum chambers that are being prototyped in the Institute of Plasma Research in Gandhinagar. There is a computing center in Ayuka, and this is an actual site where some construction is happening, and this is the engineering diagram of the final site, which is currently a CAD drawing. At the same time, the international community is also planning to build the next generation of gravitational detectors. This is primarily in the North America and Europe. And the European concept is going underground and building a triangular type detector. And the American concept is building a LIGO, which is 10 times more bigger than the existing LIGO. But in summary, they will be able to have sensitivities a factor 10 better than the existing detectors. And this shows the observing horizon of these detectors as a function of the mass of the binary. So they can reach to cosmological redshifts of several tens, which means that they will be observing practically all black hole mergers in the universe, because it's anything after star formation is something that they should be able to reach. So if they are built, and hopefully they will be built, they will be remarkable observatories which would measure practically all mergers in the universe. At the same time, let's also remember that just like electromagnetic waves, there is a whole spectrum of gravitational wave frequencies. And it can span, this wavelength can span the size of the whole observable universe and to extremely small wavelengths, high frequencies of several tens of kilohertz. And there are potentially astrophysical as well as cosmological sources in all these frequency bands also. And a lot of these frequency bands are also probed by either current or planned detectors. So for example, just below currently these high frequency band is being probed by LIGO and Virgo and Kagra, etc. These next lower frequency band of about decihertz detectors, decihertz, about 0.1 hertz or 1 hertz. There are very interesting concepts to build these decihertz detectors, and one idea is to build a LIGO in space. It's a very ambitious concept. And second is a very interesting idea, which is simpler, which is to use the moon itself as a detector of gravitational wave. So the idea is that when these gravitational waves propagate, the solid bodies basically vibrate according to the normal modes if there's a frequency matching. So this will introduce this normal mode oscillations in the moon, and if you plan seismometers on the moon, you can read out these as seismic motion of the moon. So that's the idea of these moon-based detectors also. So all these are fairly in the early stages of conceptualization and design, but there are very interesting ideas. In the slightly lower frequency band of about millihertz, there is an already planned project called the LISA, which is headed by the European Space Agency. The idea is to have 3 detectors which operate as a triangular configuration. It's an interferometer, which is about arm length of about 5 million kilometers. And using this interferometry, they can detect gravitational waves produced by mergers of supermassive black holes about million to a billion solar mass, and so on, and white dwarf binaries in our galaxy, etc. It's an ongoing project. It is funded, and it's very actively being pursued in Europe, and it's a planned date is somewhere in the middle 2030. No, it has a very interesting kind of cartwheel orbit. Yeah, it is.
You want to keep 3 objects stable, right?
Yeah, no, it's yeah. So yeah. They have found this cartwheel kind of orbit, which is actually stable, and because of this motion, it improves the angular resolution, etc. So it's not one of the standard Lagrange points. Yeah. I am not sure. Let me find out and get back to you. It's slightly trailing the Earth's orbit, but following the Earth's orbit also. I don't exactly remember, but we can find. I'll find out. Yeah, the separation is 5 million kilometers, but I don't know the distance from the Earth. Yeah. Even lower frequencies, about nanohertz, the timing of millisecond pulsars is also a very promising way of detecting gravitational waves of about nanohertz. So the idea is that these millisecond pulsars are rapidly spinning neutron stars, which have very precise rotation frequencies. So they can be treated as very precise clocks. And we observe these pulses coming from a number of pulsars, and you can model these pulsars. And the idea is when this gravitational wave passes through the Earth, there will be a delay in the arrival time of pulses. And if you monitor a large number of its millisecond pulsars, there will be a coherent delay in the arrival times of many pulsars, which is a signal of gravitational waves. And there are several international consortia that have been pursuing this. In particular, there is also an Indian consortium, and here your colleague here, Manjari Bagchi, is an active member of this Indian consortium, and they have made important contributions to this ongoing data analysis and result, which have found some very interesting evidence of gravitational waves, stochastic gravitational waves in their data. And with more data, which will come in the next few years, these detections will be confirmed or refuted in the worst case. But it's a very interesting frontier to probe these nanohertz gravitational waves. Now, the lowest frequencies here are basically the sizes with wavelengths comparable to the size of the observable universe. This can produce basically specific imprints in the polarization of the cosmic microwave background radiation. And this idea has been around for a while, and there are many experiments done using primarily Earth-based and some space-based ones, and but none of them have found a conclusive evidence of gravitational waves yet. And we have an active Indian effort led by Dheeraj and colleagues here to build a space-based observatory. This is called CMB Bharat. It is of course an ambitious project with the timeline of next couple of decades, and the idea is to precisely measure the polarization of the CMB to detect the gravitational waves in these extremely long wavelengths. So to summarize, all these different detectors would basically probe deeper and wider the spectrum of gravitational waves and hopefully uncover a lot of very interesting phenomena and new understanding of the universe in the next couple of decades. So let me summarize. The recent observations of gravitational waves by LIGO and Virgo have opened up a new branch of observational astronomy. We are already observing hundreds of signals, and the next decade this will be getting to thousands of signals because these detectors are improving their sensitivity in a step-by-step way, and the number of detections actually rapidly increased by a rapid power of these, the sensitivity. The new detectors are coming up, especially for our community. It's more exciting to see the LIGO India coming up, and it also would be associated by the upgrades of the existing detectors like LIGO, Virgo, etc. There are also ongoing efforts to build the next generation of detectors, the so-called third generation detectors from the ground, which would see practically all the mergers in the universe in a particular frequency window. There are also ongoing efforts to expand the frequency spectrum of gravitational observations to basically capture a much broader band of gravitational waves. So let me stop here, and thank you very much for your attention.
Thank you, Professor. Thank you, Professor Ajith, for giving this brilliant overview of gravitational wave astronomy and cosmology, and especially discussing LIGO India's efforts. So I have one question, but before that, we can ask the students and other. The floor is open for questions. Yeah.
So like there was this I don't know if I like heard it wrong, but like you said that there are like confirmed sources of like gravitational waves. So how do we know that there will be like thousands of like waves? Like are there like visual
No,
used?
good
It's
question.
just statistical.
That's right, yeah.
Okay.
So
Okay.
the idea that we know that because we have, how to measure the sensitivity to the detectors, and we can compute the gravitational wave amplitude. We have a reasonably good understanding of how far of the local universe we can observe. Right? If there is a merger happening in certain part, about 2 gigaparsec of the local universe, we will see it. So we have our observing volume, and in this observing volume, we have observed so many mergers. So this will give us a way of inferring what is the merger rate of black holes in the local universe. Now we can project what will be the sensitivity in the future and the corresponding increase in our space-time volume. So we will make a projection of what will be the event rate for the future.
So you're just like statistically predicting that
Yeah.
there will be more, not
Yeah.
like we see any visual
No,
cues or
no,
something.
no,
Okay.
yeah. Because there is no other way of seeing such binary black holes, right? The gravitational waves are the only way of seeing binary black holes.
I think there's this idea with like ice cube that you can see like there's some correlation with like the direction of neutrinos and like.
So these are single supermassive black holes are creating matter.
Oh no like for supermassive binary black hole mergers like at least there's this idea that like they will produce like neutrino jets that can be detected in ice cube. There's some sort of
Why do you need a
is what
binary
I've
for
heard.
that? What is lacking in a single black hole?
I don't know. Like, I'm only saying that because, like, one of my friends works on something similar to that. So, like, he works on, like, binary black hole mergers and, like, how, like, whether we can see a correlation between.
Yeah. Now, it would be interesting to see if there is a neutrino counterpart, binary black hole mergers, but I would imagine the neutrino flux is so small that it would be possible only for maybe a small fraction of such observations.
That is possible. They only, like, I don't think, like, whatever he's doing, he's only looking at, like, visual cues and then, like, seeing if, like, they match. But like there's also like when you look at it visually, there's problems with like them possibly being pulsars and like other things as well. So I don't. I was just asking.
I see.
Because.
So, is inter here?
Yeah.
Yes. Is interferometry the only way to measure gravitational waves, or is there any theoretical idea for measuring gravitational waves? Any other idea?
No, most of these methods I discussed later part, they are not using interferometry. Pulsar timing is not interferometry. CMB polarization is not interferometry. But the rest are interferometry. But there are actually a lot of very interesting ideas of lab-based detectors are being proposed now. Again, historically also the first idea was using these resonant bars. You have a large monolithic bar and it would vibrate to certain resonant frequencies, and when these gravitational waves, it would resonate with that frequency. And there are different versions of that have come out now using, for example, large magnetic fields, for example, how these magnetic fields could be perturbed by gravitational waves. There are solid state devices being proposed. All of the new ideas are coming up, but they are yet to show their promise, but there are very interesting ideas coming out.
Hi, thanks for your talk. So when you showed the numerical relativity results, especially near the chirping,
Yeah.
so is the effects of this gravitational radiation and the back coupling of it, is it also included in this kind of formalism that you have?
Yeah, I mean like the scattering of gravitation in the background and the
And also the
thing-
back coupling of the radiation on the, like for example, we have radiation damping in electromagnetism.
Yeah, of course. Okay, yeah.
These are all
the entire inspiral is due to the radiation reaction.
okay.
But here you see much more nonlinear effects also. For example, gravitation waves get scattered by the background geometry.
Okay.
It's called tail effects. And the gravitation waves get transferred scattered by the gravitation waves themselves. The gravitation waves are sources of gravitational waves. There's all kind of nonlinear effects in this picture.
And is it a controlled way of doing things like in numeric?
There is a systematic expansion called post-Newtonian expansion where you can see all this as order by order.
Okay.
But the numerical relativity is supposed to contain all that effect in a single go. Yeah.
And another question I had is you mentioned about this INPT and nanohertz gravitational wave.
Yeah.
But these are due to the stochastic location of these spinning neutron stars, right?
No. Okay. The sources are not neutron stars. The sources are
Pulsars?
no. The pulsar is just a detector.
Okay.
The sources are most likely a large number of supermassive black hole binaries. So there are a large number of supermassive black hole binaries operating at different frequencies. So all these sine waves kind of add up to produce a stochastic background. That is the simplest model, the idea. But the neutron stars are just used as a detector. Basically, they are just used as clocks.
Okay. Now I was asking you more because there could be also nanohertz gravitational wave from the cosmological phase transitions.
Yeah.
So how can we distinguish between
Okay.
these?
Not possible. Yeah. Okay. If there's a clear spectrum difference in the prediction of the spectra, it is possible. So hopefully, then these nanohertz PT observations should be in the future should be able to reconstruct the spectrum of the observed gravitational waves. Then you could ask what kind of sources could produce these spectra. I said simplest because this is mundane astrophysics. You don't have to invoke more complex fundamental physics, but it is very well possible that it is produced by something more exotic than this.
Thank you very much.
So, in slide number 20, you'd shown that, is there any reason why that curve extends beyond the point of collision? Like those two curves, the relative.
It should not extend. It's just a plotting artifact.
Okay.
Yeah. But actually, there is a slight issue here because we don't know exactly when the collision happens, right? Because there is an issue of coordinate in a gauge choice here. In a numerical relativity simulation, you can say that this collision happens at a particular time, but that time need not be the time that we see as an observer. So there is a little bit of trick confusion to map how does that coordinate time with the time that we see as an observer, but it roughly matches. But yeah, this plot is roughly meant to be just for an illustration, while these are the thing that you would observe.
Okay. Then in the last slide, you had there was this thing like for extending the capabilities of this detector. There was this thing Voyager was an A hash. How can Voyager be upgraded?
No, okay. So it's not the same Voyager. Sorry, this mission concept is called Voyager. Sorry, it is not the Carl Sagan Voyager.
Hello. So I had a question regarding, you mentioned that from observations we know that gravitational lensing effects are not uh, affecting the signal. So how would the signal be different if there was lensing?
Good question. So this can have two different effects. For example, if the lens is a very massive object like a galaxy or a supermassive black hole, you would see this so-called strong lensing. And the equivalent of that is that you would see multiple images of the same galaxy, etc. Typically, you see it in the electromagnetic waves, right? Then you see this multiple images of the same galaxy and so on. So this is very commonly seen in the optical observations. The equivalent of that in the gravitational waves is that you will see multiple copies of the same signals coming at different time. That's one thing. So the fact that we are not seeing that is used to make this constraint yet. And in this diffractive regime, if your lens is like a black hole of about 100 solar mass, then essentially this gravitational radius of this black hole is comparable to the wavelength. It is like an experiment, like a double slit experiment where the slit width is comparable to the wavelength. So you see diffraction effects. So you should see a deformed waveform that is different from an unlensed waveform. And we can compute that, and again we have done searches for those ones. We have not seen any such diffracted waveforms, so that can be used to put an upper limit on these number of
But the
events.
resolution, I mean, in future experiments, are these resolutions to sort of...
We would never be able to resolve them in the sky, but we have extremely good temporal resolution. We measure the time series of the data, and that is our strength. So we won't be able to make images of multiple galaxies, but we see them as separate signals in the data, time series data.
And one more question. So, like from the dark matter front, we know bullet cluster is a very strong evidence of dark matter.
Yeah.
It also involves two galaxies
Yeah.
spiraling about each other. So, do people also look for gravitational waves in these kind of bullet clusters? And because there we know dark matter.
Yeah, so it turns out that okay, they are in principle sources of gravitational waves, but the dark matter halos mergers are probably not strong enough to produce very strong sources of gravitational waves. However, if these galaxies also have supermassive black holes inside them, when these galaxies merge, their supermassive black holes will also merge.
And they can,
So that can be seen in the LISA in the next decades.
and for our galaxy, these are the observations, like the LIGO observations are from our galaxy.
No, all our observations are from extragalactic. They are from hundreds of megaparsecs away.
Okay. Okay, thank you.
We have not seen a galactic source yet.
And the spin distribution that you talked about, maybe I don't know the observer, but what does it mean by negative spin?
Okay, this is not the particle spin. This is the spin angular momenta of a black hole.
Yeah.
And it's normalized to the units of mass square.
Okay.
So it is a dimensionless value from 0 to 1.
Yeah.
It's a spin magnitude. But now it's a spin vector. So if the orientation is with anti-aligned with the orbital angular momentum, we call it negative. So it's an orientation thing.
Thanks.
Actually, same question, sir.
Hi. So just a question regarding, so you said that these observations are made intergalactic, right? Like
Yeah.
the sources are in a different galaxy.
Yeah.
So the gravity waves has to pass through a lot of intergalactic matter. So what is the imprint of that intergalactic matter on the gravity waves, or like how do you incorporate those effects?
Practically nil, because this gravitational waves coupling is extremely weak to the matter. So they just go through everything else. The only thing that you can couple to the gravity in a sensible way is the gravity itself. So that's the gravitational lensing. So if you have a massive object which curves the space-time in a significant curvature of space-time, that can bend these gravitational waves, that can diffract the gravitational waves, etc. So that's practically the only effect that we would be able to see. In principle, there are these extremely tiny effects to the matter, etc., but it's very hard to measure, extremely hard to measure.
So they are not imprinted on the signals that we observe.
Yeah.
And you mentioned something about gravity wave observations being a strong test for GR in extreme gravity situations.
Yeah.
But at the end of the day, when we measure the gravity wave signal, we are only doing a perturbative analysis, right?
True.
So like, how strongly do we know, like at the point of merger, or like just at the ring down phase, I think it's called.
Yeah.
Like how well our analysis matches with the like actual
Yeah, so the imprint of the source of gravitational waves contains strong gravity, right?
Right, yeah.
And hence the dynamics of the system is affected by strong gravity.
I see.
So its frequency evolution contains imprint of that.
I see.
So even though the amplitude here is very weak, the frequency evolution or the shape of signal contains imprints of the strong
So
gravity.
we do understand the later phase
Yeah,
very
yeah.
well
Yes,
as well.
yes.
I see. Okay.
Yeah, by a combination of numerical relativity and analytical methods.
Sir, is there any place where general relativity failed in the observation, whatever you did? Where do we need any quantum in, like, quantum also in that? Or any place like,
There should be many places where this fails, and some of the examples are, for example, what happens in the interior of the black holes, very close to singularity, right? We don't know, the GR doesn't work here, the classical physics doesn't work here. Similarly, the Big Bang singularity, when in the very early, the origin of the universe itself is a singularity. So these are the obvious places where both there's extreme gravity and there are sizes are quantum scale. So we don't know what the physics is
in
yet.
our data, like in our data where we can't interpret?
No, currently we don't have any data pertaining to those regions because black holes, the singularity is covered by the horizon. Again, the Big Bang singularity is also, we don't see. The earliest thing we can see is the CMB.
Understand the fluctuation in CMB using gravitational wave. I mean, early universe gravitational wave. You said it is very high wavelength.
So your question is that from the CMB, whether we can understand?
The fluctuation in CMB.
Yeah, from the fluctuation in the
Yeah,
CMB, whether
we
we
can
can understand
using gravitational waves.
Okay, so in the CMB, we are looking at the photon temperature fluctuations. They are polarized as well. Now we have also measured the polarization. So the polarization has two parts, E and B mode polarization. Okay, one is curl free and one is divergence free. So the B mode polarizations at the largest scales are supposed to be or theoretically expected to be coming from the tensor modes or the primordial gravitational waves. Okay. So those are not like larger gravitational waves that Professor Ajith has talked about, but those are the signals that he has talked about by the bicep thing. We are yet to see those. We have only found upper bounds that we have not seen up to this level. Okay, so it may be there, and that is where these are the patterns we are expecting. And if we see that in future, we will be able to say that what is the energy scale from which the universe started inflating and things like that. So we can learn a lot about the universe or the earliest time in the universe can be probed through such kind of things. But it is very difficult, and there is a big community that is working, international community that is working with the different types of observation, like ground-based and space-based, as Professor Ajith has mentioned. Yes, the bicep measurement said that the tensor to scalar ratio was of the order of 0.2, and correspondingly, if you want to translate that into the energy scale for M square phi square model, the quadratic potential, it was turning out to be 10 to the 16 GeV. But what happened is that bicep had claimed that based on a single frequency measurement. Later, when Planck worked with them, it is called bicep cake and Planck results, they found that if you use multi-frequency observation, those were actually coming from dust polarization. So when you add the dust polarization, so it was actually this kind of physics that was not included in the observation. So it was completely explained by the dust polarization, and the signal from 4 sigma, 3 to 4 sigma, came down to be completely consistent with the 0. So it was really, so there was a book by Professor Brian Keating, How to Lose a Nobel Prize. So one can look at that. But yeah, it was the first detection of the dust polarization, but anyway, it was a systematic.
So I guess this plot is correct, but the interpretation is wrong. That's
Exactly.
It's entirely the foreground that is contributed to that. Yeah. Yeah.
So, are there any more questions?
Yeah.
Okay, if not, okay, yeah, you have.
About the neutrino observation, sir. If there any disturbance by the sun?
For the neutrino observations.
Yes, sir.
So the neutrinos, the sun is a very copious source of neutrinos,
Yes, sir.
but their energies are like MeVs, while the ones that I talked about were hundreds of GeVs, right? Ice cubes. So they don't. You have an expert sitting next to you, so you can ask her more. Do you want to add? Do you want to add anything more, Indoli?
What specifically do you want to know?
Like how they are differentiated
How they are different from?
from the sun neutrinos, so the solar neutrinos.
So is ice cube
How
affected by the solar neutrinos?
Okay. See, there are many things. One is the source, one is the observer, right? So you have to make a decision because you cannot build a detector which detects everything. Right? So our eyes only see visible light. So the experiments which are neutrino experiments are designed to see certain energy ranges. So ice cube sees, because of the structure of ice cube, he said, no, you drop those photomultiplier tubes in water and the distance between them is very large. So do you know this Cherenkov radiation?
Yes, ma'am.
Yeah, so the Cherenkov radiation travels in pure water about 60 meters. So the distance between the photomultiplier tubes is optimized so that you get the maximum energy possible of the neutrino, which means that you're going to leave out the minimum energy parts. Okay, so among the lowest energy spectra, I mean, of course, leaving out the cosmological neutrinos, which are very, very low in energy, the solar neutrinos are MeV in energy. Supernovae neutrinos are like tens of MeVs, maybe 40 MeV in energy. If you look at atmospheric neutrinos, they are GeV in energy. So most of this will not be seen by ice cube. They are looking at hundreds of GeV, TeV, very, very high energy.
Would we be able to see some lensing signatures in the new upcoming detectors? For example, let's say LISA as well, or India LIGO detectors?
Yeah, no, I think the best bet would be these ground-based observatories. So we are very much hoping that this would happen in the next 5 years, because roughly the lensing probability is something like 0.1%. So if you observe order 1,000 events, one should be lensed, and that is, we are in that regime very soon. Yeah, you're waiting. But no, but yeah. But luckily here our event rates are going to increase in some sort of exponential. Yeah, true. Yeah. Which one there? Yeah, no, that is high. Yeah, that is high. Yeah. No, it is primarily the classification is based on mass measurement. In principle, we should see a tidal imprint of tidal deformation in also neutron stars also, but it is very weak imprint. We don't have signal noise ratios to see that yet. So that there is a way of, if you have a high SNR signal, there should be a way of distinguishing between black holes and neutron stars. But currently, it's based on mass ranges. Okay, so if you, again, what happens is for these low mass binaries, which could be neutron star, the ring down is at very high frequencies where you don't have good enough sensitivities. So yeah, if you are able to measure the ring down, that of course it contains that imprint.
So because ma'am mentioned about waveform templates, so I did matched filtering once. It's a very basic analysis, but so for example, when we see a CBC signal, right, we usually have a waveform template and we measure the detected waveform with that, and if it matches, it's a signal. What if the signal we are looking at is actually a gravitational wave signal but is not there in the waveform template bank?
Yeah.
Then how do we detect if how do we know it's a gravitational signal?
Yeah, good question. So that's why we have different kind of searches. These CBCs, compact binary coalescence searches, use specific models of these compact binary coalescences because they give you the best sensitivity for those kinds of signals. But we also have model agnostic searches. For example, the searches look for some sort of excess power in the data that is coherent between different detectors. So you look for coherent excess power between the different detectors without assuming waveforms, etc.
Right,
So,
right, okay.
so these are of course less sensitive as compared to signals which where we have precise models of, but there are such alternative methods also.
Okay, thank you.
So we will, yeah, if there are loud signals, we will see them, but there will be some loss of sensitivity because we don't know the correct model of such exotic possible sources.
Great. Any other questions? Okay.
So electromagnetic wave have redshift. Similarly, the gravitational waves also have similar
Yes.
phenomena.
Exactly the same thing. And actually, it's very interesting. It's an additional complication also. In the case of electromagnetic waves, we are able to measure the cosmological redshift because we can make those emission or absorption lines in the lab, and we can compare them how they are redshifted. And that's because there is for example, a specific emission line for certain elements, etc. Right? So absorption lines. But it turns out that in the gravity there is no such scale. Everything is scalable with mass. So your redshifted gravitational wave signal is equivalent to an unredshifted gravitational wave signal with a higher mass. So because you're stretching this signal to a longer wavelength, so your time scale is increased by by some factor. And in a gravity, if there's a mass, the corresponding time scale is gm by c cube. So it's probably a bit hard for you to match, but this is weird degeneracy that a redshifted signal would appear as a more massive binary to our data. So we measure what is called a redshifted mass.
Good.
Yeah. We won't see the distance. Yeah. Well, we can actually, so we can do it by assuming a cosmological model because we measure distance. So you measure distance and the redshifted mass. So you use the redshift, assuming cosmological model, convert to redshift, and do the redshift. That's what we do now.
But then the H0 measurement will depend on the cosmological model. It will not be a model.
Right. So that's why you need to have an independent measure of the redshift.
For the electromagnetic counterpart, it should be there.
In principle, if there is a non-gravity signature in the signal, we're going to do it. For example, the nuclear physics, and the nuclear physics is well understood, there is a scale there. So one can use to break that degeneracy.